Hello everyone, we are Group 15. I'm Bunket. Today we'll present our case study on distillation column design. As an introduction, distillation column is a unit operation used to separate various components of a liquid mixture based on the difference in volatility. A typical distillation column consists of a column, condenser, reflux drum, and a deboiler. Next, we will move to process design. Methanol is to be recovered from aqueous feed stream using a tray column. The composition of methanol is set to be 0.93 in distillate and 0.01 in bottom. Since the stream composition are given as molar ratio, hence it is required to convert the mass flow rate of feed stream to molar flow rates. Next. From the overall material balance and component material balance, we obtain two simultaneous equations. Solving the equations, we will obtain D and B, distillate and bottom. Next. To determine the number of stages, we use the MATCAP-TD graphical method. First, we plot vapor-liquid equivalent data as a blue curve on the diagram. Given that the feed is a saturated liquid, we draw a vertical line at x equals to 0.2. The intersection between the Q line and equilibrium curve gives us a pinch point. Next. By substituting the pinch point into the minimum reflux ratio equation, we obtain R mean equals to 0.921. Given R equals to 1.5 R mean, we obtain the operating reflux ratio equals to 1.38. Now we can plot the rectifying section operating line RL, which is shown as the gray colored line on the diagram. Next. The stripping section operating line is drawn from x equals to xp to the point of intersection between the Q line and RL. Now we can start counting the number of stages from x equals to xb to x equals to xd. In total, there are 9 theoretical stages, including the partial reboiler. Feed stage is located at stage number 4 from the bottom. Given column efficiency equals to 0.85, we obtain the number of actual trays equals to 10. Next, I will pass to Charmin to continue.
Okay, so I'm going to talk about the physical column and the plate hydraulic design. So first, we are comparing between the three common tray types, which is sieve, valve, and bubble, against a different parameter. The optimum condition is highlighted as bold, and as we can see from here, the sieve tray is shown as the most suitable type. Next, we will calculate the plate hydraulic design. To calculate it, we need a few sections of calculation. The first is the flow rate. Based on the information obtained from the previous part, we can calculate the vapor flow rate and the liquid flow rate above and below the feed. So the second part is the physical properties, which in this section we will calculate the pressure drop, and by assuming the pressure drop per plate is 100 millimeter of water and take a reference of the atmospheric pressure. And for the molecular weight and the surface tension, we need to simulate the condition at the S1 high seas. So the third part, we will calculate the column diameter. We will use the FLV value and the figure 11.27 to obtain the K coefficient. However, the K1 coefficient has a limitation of surface tension of 0.02 Newton per meter. Hence, comparing to our real surface tension obtained, we need to do a correction on the K1 coefficient. So by using the information obtained above, we calculate the flooding velocity, the maximum volumetric flow rate, and the net area and the downcomer area. By using the area, we can calculate the column diameter. We're assuming that the bottom and the top column diameter is same, so we take the largest number, which is 0.985 meter, and comparing to the commercial available pipe size BS1600, and take the standard thickness 9.52 millimeter, we obtain the inside diameter should be for commercial range is 1047.75 millimeter. We take this number for further calculation. So moving on, we calculate the liquid flow pattern and the professional plate design. For the liquid flow pattern, by calculate the maximum volumetric liquid rate, we comparing the figure 11.28, we know that the flow arrangement should be single pass flow. And also, we consider the assumption given in the assignment instruction, which the ratio of the wire length to the column diameter is 0.76. The downcomer area to the column area is 0.12. We can obtain the following parameter value. So next is the whipping. By assuming a turn down ratio at 80%, we can obtain the maximum and the minimum liquid rate and also the wire crest. By sum up the wire crest and also the whole area, we can refer to figure 11.3 and obtain the K2 coefficient. And then we can calculate the minimum vapor flow velocity, which the calculated result show that is above the weak point vapor velocity, which means that our assumption to the whole area to the net area is acceptable. So next, we are calculating the plate pressure drop, which is a total of the orifice loss and the static head of liquid on the plate. So by obtaining the orifice coefficient from figure 11.34, we can calculate the dry plate drop and the residual head. And we sum out it together with the wire crest, we can obtain the total pressure drop. Next, we will calculate the Dow common residence by using the formula given here. So, which this result 6.776 seconds is greater than 3 seconds, which means that the time is enough to prevent the accumulation of liquid. And using the following formula to calculate for the entrainment, which we obtain that the entrainment is 0.55, which compared to the optimum is 0.1. However, it's actually acceptable for the optimum design value to be above the given value as long as it's below 1. So we're moving on for the perforated area. By refer to the figure 11.32, we can calculate the perforated area, and taking the ratio of the whole area to the perforated area and refer to figure 11.33, we can obtain another ratio number, which is the perforated length to the whole diameter 2.7 compared to the given to an optimum value, which is 2.5 to 40 for, according to the reference textbook. 2.7 is in the acceptable range for a high efficient distillation process. And next, we calculate the number of holes. And here, until this stage, the plate design is completed. I will pass it to Jin Yang.
Okay, thank you, Jiaming. I'll talk about the mechanical design, and for the mechanical design, general design consideration only will be included for the purpose of the case study. Next slide. So the first consideration will be design pressure and temperature. Recall from the previous sections, the highest operating pressure that we have is 1.11 bar, and the highest operating temperature is 90 degrees Celsius. Hence, with the safety margin of 10%, the design pressure will be 1.23 bar, while the safety margin for design temperature is 50 degrees C, and the design temperature will be 118 degrees Celsius. Next slide. The second consideration is design stress. The maximum allowable stress of the material chosen is determined to verify the acceptance of the material. So in this case, the hydrostatic test pressure is considered. It is calculated by the equation shown here, and which the value can be obtained from table 13.1 and table 13.2. Next slide. The third consideration is welded joint efficiency. The joint type and welding quality are the two main factors that affect the strength of welded joint. The common welded joint efficiency is shown in the table. For this design, double welded butt joint will be used because it is the most basic type of joint and has highest efficiency. Next slide. The fourth consideration is wall thickness. To get the wall thickness, the material used for vessel has to be specific. So here, ASTM A516 grade 70 carbon steel is used after comparing different materials. All of the standard parameters are shown in the table for the wall thickness calculation. And recall from the previous sections, the internal diameter of the column is 1.048 meter. First, the minimum thickness is calculated using the formula shown. At a allowance of 0.2 cm, the thickness of the wall will be 0.47 cm. Hence, taking into account the wall thickness, the outer diameter of the column will be 1.057 meter. Next. The next consideration is head enclosure. After comparing different type of head enclosure, Torus spherical is chosen because it is easier and cheaper to fabricate. The parameters and equations needed in calculating the design of head are shown in the table here. Next. The sixth consideration will be design load, and design load is divided into major and minor groups. For this case study, only the weight of vessel and content and wind loads will be considered. Detailed equations and method of calculation will not be discussed here. The blue table here show the weight of vessel and content, while the red table show the wind load. And the parameter of interest will be the total weight and column-based bending movement due to wind load. Next. The last design consideration for mechanical design will be column support. Skirt support was selected as the vessel support because distillation column is tall and vertical vessel. The material constructions of the support will also be carbon steel because it is cheap and have high strength. The details design of the support are shown in the table here. The skirt thickness design is valid because both the parameters shown in the design criteria is larger than tensile and compressive stress. Next, I'll pass to Amin.
Thank you. Moving on to the utilities, safety considerations and process control. Next. Speaking of the energy balance around distillation column, the assumption made is that the total condenser is used with a partial repolar in the separation process of methanol and water. The condenser and repolar duties are calculated and it found that 1,886.04 kilowatt for the condenser and 1,968.4 kilowatt for the repolar. And the utilities used to accomplish the temperature steady state conditions in the top and bottom of the distillation column, according to Aspen Energy Analyzer, is that a cooling water at around 30 degrees C will be sufficient enough to provide a cooling in the condenser to get the distillate with around 40 degrees C, and intermediate pressure steam at around 175 degrees C will be sufficient enough to provide heating in the repolar to get a bottom product at around 90 degrees C. Moving on to the material safety considerations, since the distillation column is producing methanol and is considered one of the highly flammable liquid and highly toxic substance in the environment, it is important to consider safety procedures that in terms of handling and storing methanol to avoid any health and environmental hazards. To mitigate these potential hazards, it has to be stored in proper conditions and strict measures. Second, following the emergency response plan in the case of any accidents occur in the plant to alter the operators in the plant as well as the surrounding community. Lastly, wearing a personal protective equipment when handling methanol. Next. Speaking of the process control and instrumentation, indeed there are many control loops has to be considered when design distillation column, such as level control loops in the condenser, reflux drum, and repolar, as well as the flow rate control loop in the feed stream. However, in this case study, we only focus in three main column internal parameters: temperature, which is controlled by manipulated the steam flow rate into the repolar with a control temperature control set point of 90 degrees C. Second, pressure, which is controlled by manipulating the flow rate of cooling water into the condenser with a controller set point of 1 bar. Lastly, reflux ratio, which is controlled by manipulating the reflux flow rate into the distillation column with a controller set point of 1.38. Thank you. I'll pass to Wenhan to continue.
So now I'll talk about the back cost estimation. For the back cost, next slide. For the back cost estimation, we are using values taken from the book Analysis, Synthesis, and Design of Chemical Processes, where the equipment type for the towers is based on the tray and pipe equipment, and the trays is based on sieve trays. The Chemical Engineering Cost Plant Cost Index (CEPC) was used to update the cost value, as the CEPC value in the referred appendix was based on 2001. For the cost estimation of the tower, the price will be split into two sections: the bare module cost of the tower and also the bare module cost of the tray. The difference between the purchase cost and the bare module cost is that the bare module cost includes the direct and indirect expenses for the purchased equipment. As such, with a material factor of 1 for carbon steel and a calculated pressure factor of 0.6087, the bare module cost of the tower is Rm 22,342. For next slide. For the cost estimation for the cost of the tray, we will be using a quality factor of 1.64, and we'll obtain a bare module cost of 90,286. Combining both of the bare module cost, which is the bare module cost of the tray and also bare module cost of the column, we will obtain a total bare module cost of 112,628. Next slide. And finally, I will conclude the presentation slide. So for our process design to achieve 93% purity methanol at an 80% turn-down ratio, we will require a 10-stage distillation column with a reflux ratio of 1.38. As shown on the slides is the plate design and column designs. And for the mechanical design, we'll be using carbon steel due to its low cost and high strength. A skirt support was also chosen for the distillation column. And finally, a cost estimation of 112,628 was calculated for the cost of the distillation column. Thank you.